Okay, so today's review lecturer is Yolanda Lozano from the Universidad of Oviedo, and Yolanda is going to talk about gravitational solutions, quivers, and the AdS CFT. Thanks.
Thank you very much, Gabriel, for this opportunity to speak here. I have to say that this is a bit challenging for me because this is a very diverse audience, and I don't know, the subject is rather technical, so I hope I reached the right equilibrium, but we will see. So I'm going to discuss some aspects of gravitational solutions, quiver gauge theories in relation with AdS, and plan to start giving some introduction, quite basic introduction to dynamics, to the formulation of the CFT correspondence. And then from there, I will move on to discuss so-called Hanani-Witten brane setups, brane configurations where you can in particular realize the AdS CFT correspondence. So we will introduce these configurations and present some examples, and also the AdS solutions that describe holographically the field theories that we will see live in these Hanani-Witten brane setups. Then I will consider a very explicit example because I would like to show you how given a geometry which is associated to some Hanani-Witten brane setup, one can construct the quiver gauge theory that is associated to this geometry. And this quiver gauge theory describes a conformal field theory in some regime, which is dual to this geometry that we considered at the beginning. And this, I will use it to check the AdS CFT correspondence in the particular example of AdS3 CFT2 pair that I will discuss in detail. And then I will give some conclusions. So this is like a very introductory talk in some parts. In some others, it becomes more technical, but you are free to interrupt me at any time. There is no plan, I have to reach there. So the better you understand, the more you understand, the better, and it doesn't matter whether we reach to the end or not. So introduction. Well, string theory contains BPS saturated solitonic objects of different dimensionalities that we call p-branes. These are solitons, these are configurations of finite energy that appear as solutions of the equations of motion, which are non-perturbative. And when we say they are BPS saturated, is because they satisfy a bound that is imposed by the supersymmetry of a string theory that imposes that their energy or their tension must be equal to their charge. So this is a strong constraint. These objects, I say, come with different dimensionalities because string theory lives in 10 dimensions. So we have room for this kind of objects with different dimensions. They all have room in string theory. They are called p-branes, where p refers to the number of spatial directions of the object. So this already this bound that they have to satisfy that the energy must be equal to their charge. And some other properties are protected by supersymmetry. And this is nice because you can access some information in the strong coupling regime by doing computations at weak coupling, because supersymmetry guarantees that whatever you are studying, not whatever, some properties of the solitons that you are studying at weak coupling will be preserved into the strong coupling regime. So typically in string theory, the fundamental object is the string. This is a one-dimensional object. And the soliton that is electric magnetic dual to the string in the 10 dimensions in which a string theory lives is a 5 brane. It is the so-called Neve-Schwarz 5 brane. This is the normal soliton. It scales with 1 over the string coupling constant square, is non-perturbative, and it has the usual scaling. But in string theory, there is room for other solitons And the especially relevant ones for what I will be discussing here are the D-branes. These D-branes come also with different dimensionalities, DP branes. They are charged with respect to some potentials that live in string theory, which if you have a DP brane, this is charged with respect to a P+1 potential, P+1 form potential. And these objects are especially relevant because they were predicted in string theory as hypersurfaces where open strings can end. So these open strings have some dynamics and they induce these dynamics into the D-branes. They are solitonic because they are also non-perturbative. Their tension scales with 1 over the string coupling constant. So they are not as non-perturbative as the Neveu-Schwarz 5 branes that I mentioned before. They are lighter. This has also some importance in what follows. But the most relevant thing about them is that since the open strings that end on them induce dynamics, we can study the dynamics of these non-perturbative objects using open string perturbation theory, with the condition that these ends of the open strings end on the particular DP brane. So this is what makes branes, D branes, very powerful. So let me say a few more things about brane dynamics. The study of D-branes has offered an unexpected window into non-perturbative physics because you can describe the dynamics perturbatively using open string perturbation theory to describe something that is non-perturbative, the D-brane. And this has led to surprising connections between string theory and gauge theory that have culminated with the discovery of the AdS CFT correspondence. This is possible because in certain limits, brane configurations, I don't say just D-branes because we will consider also intersections of D-branes, also with NS5 branes, whatever. So in general, brane configurations are described as solitons of the equations of motion that come from string theory. These equations of motion are the ones that arise at low energies. At low energies, you send the size of the string to 0, is the particle-like limit, and the equations of motion that you obtain are the equations of motion of supergravity, which are space-time axioms, are derived from space-time axioms, these equations of motion. But there are other limits in which these D-branes are described by the open strings that end on them, and these at low energies, you have to consider the light modes that come from the open strings, restricted to end on the work volume of the branes. We talk about work volume because an object with p dimensions, it swaps a p+1 dimensional work volume in the space-time. And these light modes describe gauge theories. So here is where we have the connection between string theory and gauge theory. In different dimensions, depending on the D-branes whose dynamics you are studying, and with different kinds of matter. And we will find many examples of these gauge theories through the talk. So this different way of thinking about the D-branes as solutions of the supergravity equations of motion and as the hypersurfaces where it can end is the basis of the formulation of the AdS CFT correspondence. The original formulation of this correspondence was based on the study of a stack of n D3 branes. These D3 branes live in one of the two string theories with 32 supersymmetries that exist, which are the type 2A and the type 2B. These ones live in the type 2B string theory. As I said before, they are charged with respect to some potentials that we call Ramon-Ramos potentials, and these come with different ranks in the type 2A and the type 2B string theory, such that odd dimensional branes appear in the type 2B string theory and even dimensional ones in the type 2A string theory. Well, this system of branes has two dual descriptions, as I was mentioning before, as a system of open strings or as a solution of the equations of motion of type 2B supergravity, the low energy limit of the type 2B string theory. As a system of open strings at low energies, what you find is that the gates theory that lives in the D3 branes is described by a four-dimensional, because the work volume is four-dimensional, 3 spatial dimensions plus the time, SUN, the rank of the gates group is the number of D3 branes, super-Yang-Mills theory with 4 supersymmetries. And in this description, the Yang-Mills coupling constant squared is equal to the string coupling constant that couples in the work volume of the D3 branes. As a solution to type 2B supergravity, you find that AdS5 process 5, where this AdS is anti-de Sitter space, this is a maximally symmetric solution to 5-dimensional gravity with negative cosmological constant. And this 5 is just the 5 sphere. This is a space in 10 dimensions where the strings live. And this is the space that, the space-time that arises around ND3 branes. So it was called this correspondence between these, well, now I'm going to be more precise about the relation between these two descriptions, but we find on one description an anti-de Sitter solution. In the other description, we find a theory, a super-Yang-Mills theory, which is conformal, and this is why the relation was formulated as the AdS CFT correspondence. So in this, you can look at the details of this space-time, how it arises a solution of the equations of motion, and you find that the S5 and the AdS5 have the same radius, which is given by this expression here, which involves the string coupling constant. This is what governs string perturbation theory. The n, which is the number of D3 branes, and the string length, which is the parameter that sets the size of the strings. So if you want to deal in a string theory with the supergravity description, I said that this AdS5 process 5 space is what appears when the D3 branes are solutions of the supergravity equations of motion. This supergravity description is valid, as I mentioned before, as at low energies, when you send the string length to 0 such that you are taking the particle-like limit. So the supergravity description is valid when the radius of both the radii of both parts of the geometry are much larger than LS. And if you remember this relation that I was showing here, if this R must be much larger than LS, this implies that G Yang-Mills squared, or G string times N, has to be very large. And here I have already substituted G string by G Yang-Mills squared, because this is what was defined by Toft as the Toft coupling. So in the supergravity description, this combination of the Yang-Mills coupling constant and the rank of the gates group must be large. Also, in the supergravity description, you also have not only LS going to 0, but also you are at 3 level in a string perturbation theory. This means that the string coupling constant is very small. This implies that the Yang-Mills coupling constant is very small, and therefore N must be very large such that this is satisfied. This is the planar limit of N equals 4 super Yang-Mills. As other gates theories, N equals 4 super Yang-Mills has a topological large N expansion, in the sense that you can recombine your perturbative expansion, your Feynman diagrams, in a way in which you write the perturbative expansion in this way. As a planar expansion, because when here you are summing over the genus of the surface that where you can draw your Feynman diagram. When G is 0 is N squared, when G is 2, then this becomes 1 over N squared. So this is what is called the 1 over N expansion. This resembles the perturbative expansion of a string theory, because it happens exactly in this way. In this case, with the string coupling constant. And here you have also an expansion on the top parameter that I have put just in this inside this function. So the type 2B supergravity, which is the one that we have very much under control in string theory because we know how to compute things in supergravity, is dual to n equals 4 super Young Mills in the planar limit because this has to happen, and at a strong top coupling because this has to happen as well. So this is in this sense a weak strong duality because supergravity appears in the weak coupling limit of string theory, and we are describing on the other side the strong coupling limit of the super Young Mills theory. Now, if one wants to go beyond the supergravity limit, this is much harder. This is what is called the strong version of the AdS CFT correspondence, because basically in the string theory side, we lose control about many things. But still the correspondence states that type 2B superstring theory is dual to n equals 4 super Young Mills. The surprising thing about this duality is that it is establishing the equivalence between a 10-dimensional closed string theory and a 4-dimensional gauge theory. This 4-dimensional gauge theory lives in the boundary of the AdS5 space. This you can see in a suitable coordinate system. You can write AdS5 such that the boundary is at R infinity, and here you find the 4-dimensional flat space where the gauge theory, the n equals 4 super Young Mills theory, lives. So this AdS CFT correspondence is an explicit realization of previous ideas that went under the name of holographic principle that had come out in the physics of black holes. Because here the S5 part of the space is compact and normally is left out in this discussion, but you have gravity propagating in a 5-dimensional space, but through the correspondence, its degrees of freedom are encoded in the boundary of this AdS5 space and described by the gauge theory that lives there. So this is a very explicit way to realize how and which are these degrees of freedom that allow you to describe some gravitational theory in a higher dimensional space. Okay, so one, I'm going to tell you quite generally the most direct tests of the correspondence. When I will then later consider other examples of AdS CFT dual pairs, we will be checking these things just to give support to the different dualities that I will be proposing. So the symmetries match on both sides. In AdS5 process 5, the bosonic symmetries are just the isometry of AdS5, which is SO4,2, and of the S5, that is SO6. These are also symmetries of n equals 4 super Young Mills, because when I come in a moment in more detail, which is the field content of n equals 4 super Young Mills, I will say it has 6 scalars and the SO6 rotates the scalars, also the fermions that this theory has. And then the SO4,2 is the conformal group. This is this theory I said is conformal, and therefore it's an enhancement from the Lorentz group, which is SO3,1 to SO4,2. This SO6, which in the geometrical side is associated to the isometries of the internal space. Internal is what is not AdS ether. This is also an SU4, and this is the R symmetry group of the supercharges of the n equals 4 super Young Mills. I will say this a bit more carefully later. But just to tell you that these global symmetries that you find, or these isometries that you find in the internal space, are normally the R symmetry group, which specifies for you which is the supersymmetry that you have in the dual gauge theory. Well, the supersymmetries also match because AdS 5 crosses 5 as a solution of the type 2b supergravity preserves all the supersymmetries that this supergravity can have, which are 32, because the type 2b type 2 theories have 2 supercharges, each one of them with 16 components. So this means 32. This is a maximally supersymmetric solution. And n equals 4 super-Yang-Mills is also maximally supersymmetric, because in 4 dimensions, the super-Yang-Mills theory can have a maximum 4 supercharges. Each one of them has 4 components. This makes 16. You have to add the superconformal generators, and you have 32. The central charges that I will find later, how you compute the degrees of freedom associated to the supergravity solution and the degrees of freedom associated to the dual CFT match. I will show an explicit example of that. And this is quite non-trivial, but it has also been shown that a string perturbation theory in 1/n matches all orders the super-Yang-Mills expansion. So, of course, if you want to prove the correspondence in its strong version, this becomes much harder, because we do not have a good definition of non-perturbative string theory. We don't know how to work non-perturbatively in a string theory. Rather, n equals 4 super-Yang-Mills can be seen as the definition of non-perturbative type 2b string theory on AdS 5 process 5. Of course, here I will not be saying much. But what is important is that the AdS CFT correspondence has allowed to set new light on gauge theory dynamics, because thanks to this correspondence, we have been able to study properties of gauge theories in the strong coupling regime, mostly using the correspondence in this direction, because we can use the weakly coupled description of string theory, supergravity, which is very well under our control. And this has also allowed to shed light on the quantum mechanics of black hole, because as we are going to see, this I will mention very superficially, but the correspondence has been extended to other supersymmetric cases based on the study of different brane intersections and to other dimensions. In particular, when you have AdS solutions, AdS 2, AdS 3, these are near horizon geometries of black objects, black holes, or black strings. So if you have the CFT dual to that particular geometry that describes a black hole, you can use the CFT to compute microscopically the entropy of these black holes. So you can use the correspondence, especially at low energies, to also advance on the microscopical description program of black holes. Okay, so in this talk, we will focus on the duality between AdS spaces and CFTs that will be described by quivers, with these quivers emerging from configurations of branes that are called Hanani-Witten brane configurations. This allowed to describe quite non-trivial gauge theories. I will show you how they look in the next slide, which are pictorially referred as a quiver. In this case, we will see examples of the AdS CFT correspondence with less supersymmetries than the ones that are present in AdS 5 CFT 4, which in particular preserve half maximal supersymmetry. So what is a Hanani-Witten brane setup? Well, the point is to consider a configuration in which we have NS5 branes. I told you these are the solitonic branes that are heavier than the DP branes. These NS5 branes, you take them position in different values of a given direction in the space. This direction here, that is normally referred as the field theory direction. And then you have BP branes that are stretched between these NS5 branes. You can also have additional BP plus 2 branes that are perpendicular in some directions to the BP and the NS5 branes. I will show you more precisely where, in which directions all the branes lie. But here the important thing is that this whole brane intersection, in the whole intersection, the intersecting space of the BP, NS5, and the BP plus 2 branes is on a space-time. So in the complete intersection, we should find a Gates theory, which is p-dimensional. This Gates theory lives in each of the intervals in the DP branes that are stretched between the NS5 branes. I said that the NS5 branes are heavier than the DP branes. So since we are computing the light modes, we just restrict to the light modes that appear in the work volume of the DP branes coming from the open strings that end on these DP branes. And these DP plus 2 branes that can also be there, typically in these setups, they have one non-compact direction. And this implies that they are also more non-dynamical. Well, they are frozen in a sense, in a similar way as the NS5 branes are at the low energies at which we are computing the light states that describe that lives in the DP branes. I'm going to be more specific about what I mean by this. How you see that these ones don't contribute with dynamical degrees of freedom, they don't contribute with global symmetry, providing flavor groups to the Gates groups coming from the DP branes. So basically, you have a set of Gates in each of the intervals. You can have a different number of them. This is what here is depicted by these circles. These are the SU. L1 is the number of DP branes here, L2 there, LN there. Then there are the flavor groups that these branes give, which are in the fundamental representation. This is how they are depicted in this quiver diagram. But then here we can have extra degrees of freedom, extra matter fields that come from the open strings with one end on a DP brane and the other end on an adjacent set. I say a DP brane, a stack of DP branes and an adjacent stack of DP branes across an NS5 brane. You can have an NS brane that starts if the two sets of DPs are coincident. This is farmless because it comes from the DP, these two sets of DPs are coincident. So you can have a massless string with an origin in one of them and an end in the other one. This will give what is called bifundamental matter, because these matter fields come in the bifundamental representation of the two H groups. And this is depicted in the quiver by these horizontal lines. So typically, this is the Gates theory that one can work out from a Hanani-Witten brane configuration. Now, here we are interested in these Hanani-Witten brane configurations and the role that they play in the AdS CFT duality. So for this, we would like that these Gates theories are conformal field theories. This may happen, for instance, in 4 dimensions. You can find with certain conditions that your quiver Gates theory directly describes a conformal field theory. But in other dimensions, since we have that the string coupling constant scales with the mass to 4 minus d, we can find the conformal field theory in the IR or in the UV at low energies or at large, at high energies. When D is less than 4, we have that the coupling constant scales with the energy. And in this case, we may find a conformal field theory in the infrared. While if D is larger than 4, this occurs in the opposite end, in the UV. And this if certain conditions are satisfied. We will see examples of this. Then, if an AdS solution, now if a CFT is appearing in the IR or in the UV, then we expect that there will be a solution to the supergravity limit of the string theory where the branes live that will be of AdS type close to the branes. And this will be the geometrical dual of the corresponding CFT. Okay, these AdS solutions should arise, I already mentioned this, as the near horizon geometry of the brane intersection. So you again are doing the same thing as we did when we first introduced the AdS CFT correspondence with the ND3 branes. Only now you have a more complicated intersection of branes, but you look at their near horizon, you find an AdS geometry, and then you look at the degrees of freedom coming from the open strings ending on the brane intersection, and you find out what is the Gates theory, which either by itself or flowing to the IR or to the UV will produce a CFT dual to this AdS solution. These AdS2 solutions are known, they have been identified for all types of Hanani-Witten brane setups involving DP, NS5, and DP+2 branes. But surprisingly, some of them, for instance, when P is 5 or when P is 2, have only been discovered quite recently.
So I'm sorry, I'm not very familiar with this word. You said that the P+2 was transferred to the other two branes, and when P is 5?
You have a 7 brane. You have these 7 branes.
But the E5 was between 7 and 5.
In that configuration, you have D5 stretched between NS5s with perpendicular D7 branes. I can show you, let me see if this is already here. Here is for D4s, but it would be similar. In this case, you would mean the D5 will have one extra cross here because this is where the branes lie, the crosses. The minuses is the transverse space, so you would have one extra cross here. And you would have one extra cross on the other one that is not intersecting. No, sorry, you will have one extra cross here and here in both places, because in that case, the common intersection is 5-dimensional. This is how, and you can have them also D6, NS5, D8. You cannot have more than that. But, and in fact, the D6 case, I will discuss it in some detail. Any other question? So let me see where I was. Yeah. Okay, so I already mentioned this, that the Gates theory living on the Hanani-Witten brane setup is determined by looking at the quantization of the open strings with ends on all the branes that give the brane intersection. For this, it's useful to know first, which is the Gates theory that lives on NDP branes before you add the NS5 branes and the extra stuff. The Gates theory living on NDP branes is the dimensional reduction to P+1 dimensions of 10-dimensional SUN n equals 4 super Yang-Mills. This is the Gates theory that lives on open strings. Open strings in string theory live in a 10-dimensional space, and this is the effective action that describes them. When you impose that they have to end on a hypersurface with P+1 dimensions, then you find that the dynamics that they induce is described by the dimensional reduction of this theory to P+1 dimensions. Okay, and in this reduction, the Gates theory contains a vector field It has 16 supercharges. Typically, the D branes break the supersymmetry of the space where they are embedded by a half. If you just have one set of the branes. This gauge theory contains as well 9 minus p scalars, which describe the fluctuation of the strings in the transverse space, and then some fermions. So for p equals 3, this gauge theory is 4-dimensional n equals 4 super-Yang-Mills, this reduction, which is conformal per se. Now, in 4 dimensions, it's possible to build conformal field theories with less number of supersymmetries, and you do that precisely by engineering them in Hanani-Witten brane setups. So this is one of the useful things that one can do with these Hanani-Witten brane intersections. Now, not any Hanani-Witten brane setup that involves D4, NS5, and D6, because before I said the field theory lives when we had DP branes in the P in P dimensions. So to be 4, it has to be this intersection involving D4s as color branes. These Hanani-Witten brane setups have to satisfy certain conditions to describe conformal field theories that are shown here. I will not give you more details about this, though I will refer more carefully to how you get this condition. The number of flavors in each of the intervals has to be, or this is the rank of the global of the flavor group coming from the D6 branes, has to be twice the rank of the gauge group on the D4 branes. Okay, so yeah, I'm going then to show how this happens for these 4-dimensional n equals 2 conformal field theories. So in this case, the branes live basically in a flat space, but here we have a 1,3 Minkowski space that all the branes span. The crosses are the directions on which the branes lie. The minus are the perpendicular ones. We have this interval. This interval is along the direction in which I was showing the Hanani-Witten brane setup, where the NS5 branes are located and the D4 branes stretching between them in this I direction. So the branes are, these D6 are completely orthogonal to the other two in the directions in which we don't have the field theory. The field theory lives in the intersection, so it is a 4-dimensional theory. First, let's care about the supersymmetries. I mentioned already that a set of D4 branes breaks half of the supersymmetries. The ones that they break are imposed by this condition. Then S5s break a further half. So if we started with 32 supersymmetries, which is what type 2 string theory has, in flat space, we are breaking to 16, and then we are breaking to 8. This is the number of supersymmetries preserved by the Hanani-Witten brane setup. So they allow you to reduce the number of supersymmetries because the D6 don't reduce any further the supersymmetries. The half that they would break is already contained here. Now you have to analyze the open strings that end on these different branes. So if you first consider the open strings on M D4 branes, not ending on NS5 branes, this would give you a 5-dimensional super-Yang-Mills theory, as I mentioned before, containing a vector and then some scalars and fermions. I'm not going to be too specific here. 16 supersymmetries because I didn't introduce yet the NS5 branes, and this is what n equals 2 in 5 dimensions means because each supercharge has 8 components. But now you need to introduce the NS5s. This will reduce the supersymmetry and restrict the extent of the D4 branes on the X6 direction in this one. Now the field theory living in them will be four-dimensional at low energies, because the interval on which the D4 branes are stretched, if you take, if you go to low energies compared to the inverse between the separation of the NS5 branes, you see them effectively as the field theory as four-dimensional and lives in this intersection here. So,
where it go with the dimension of the field theory and low energy is the intersection of the D and the NS5?
yes. Yes, this is by construction how it is done with these Hanani-Witten intersections. So the effective gauge coupling comes the inverse of this is the gauge coupling that lives of the gauge coupling of the gauge theory that lives in the D4 branes at low energies. And for the D4 branes, in order to obtain this four-dimensional gauge coupling in the effective action of the D4 branes, you have to integrate over this direction. Okay, and this is why you obtain that is proportional to the separation between the branes in between the NS5 branes in the given interval. I will be more precise later, including here the couplings that I set to 1, the G string and L string and whatever. Before I was saying that the D6 branes contribute just with flavor groups, because in their case, if you want to read this from the work volume of the D6 branes contain 2 extra directions, as you see here. They contain, well, rather 3 extra directions. Normally, one of them is non-compact. And then when you do this integration of the extra directions, you obtain here 1 infinity, because this direction is non-compact. So they are frozen in this sense. So this is why they contribute with flavor groups to the gauge theory that lives on the D4 branes. So now here is how you impose the boundary conditions. If you had your D4 branes and now you impose the conditions that they have to end on NS5 branes, this impose the NS5 branes impose boundary conditions on the vector and matter content of the 5-dimensional n equal to theory. And this brings you in the end a 4-dimensional n equals to a vector multiplet. And the supersymmetries here are already reduced because the notation is always a bit confusing. Here you had 2 times 8, but here is 2 times 4, which means 4 supersymmetries, while here you had 16. This is because you introduced the NS5 branes, you reduce the supersymmetry, and then all the matter content is realized in terms of multiplets with less supersymmetry. Now you also have these massless fields that I mentioned were coming from the left D4 branes, meeting the right D4 branes across the NS5 brane. This eliminates the vector from the 5D n equals to vector multiplet, but leave some scalars that build a hypermultiplet, a 4-dimensional hypermultiplet that is in the bifundamental representation. So if you have Ln D4 branes in a given interval, the gauge group is SULN. This is a 4-dimensional n equals to a vector multiplet. And then there are these hypermultiplets that are in the bifundamental representation coming from the D4 branes in the previous interval and in the following interval. And then you have, if there are Fn D6 branes, this introduce Fn hypermultiplets. Again, here you have to impose the conditions that the open strings start on a D4 brane and end on a D6 brane. This gives you a hypermultiplet, blah, blah, that is in the fundamental representation. So, no.
So, this one set up the precision combination of the running copy inside of the thing.
Yes, you can do that as well. solution in this regard with the analytic condenser. Yes, and you can learn many things about the gauge theories. I mean, they don't need the conformal character is quite special in a way. And this is what I am focusing here because I want to find the geometrical description as well, but they have been used to learn many things about cyber duality, mirror symmetry. Yes. I mean, the status of that is a whole bunch of thousands of papers, and maybe not thousands, but that would be the subject for another talk. Okay, just summing up, the open strings with both ends on a D4 stack represent gauge fields. Connecting the force stretched between different NS5 represent by fundamental matter, and connecting the D force with the D6 represent fundamental matter. And this is how you describe the whole field content. Now, this brane configuration is well approximated by the 4D gauge theory when the string coupling constant goes to 0, because you are describing the branes with the degrees of freedom coming from the open strings. You are decoupling gravity. They also interact gravitationally. So when you send this to 0, you are decoupling gravity. And now I am including here GS and LS. They come in this particular way. If you want your Yang-Mills coupling constant to be fixed, then this quotient has to be fixed. In the supergravity limit, or GS going to 0, you need to have the branes almost coincident in the supergravity limit in order to find a fixed gauge coupling constant. Okay, so now comes the part of conformal invariance. In order to satisfy conformal invariance, the beta function has to vanish. Here I'm not going to show how this goes, but if you take into account that the bifundamentals contribute to the SULM beta function as Ln-1 plus Ln+1 flavors, then you find that the beta function is vanishing at each interval if this condition is satisfied, which means that twice the number of colors, the rank of the gauge group, equals the number of flavors, the ones coming from the bifundamentals and the ones coming from the D6. This is the condition that needs to be satisfied for these theories to be conformal. And then in this case is when you expect to have an AdS5 geometry, because these are four-dimensional theories that describe these conformal field theories geometrically. In fact, these CFTs are dual to geometries that were found later on by Gaiotto and Maldacena in 2012, which are AdS5 with this internal space, S2, S1, and this is a two-dimensional Riemann surface. This should arise, I say arise, but this has not been proven because technically it's not that simple, but if you take the near horizon limit of this superposition of D4, NS5, and D6 branes, this solution, this type of geometries should arise. Here we can check again that the global symmetries of the isometries of the internal space, in this case the S2 and S1, which is SU2 and U1, coincide with the R-symmetry group of the four-dimensional n equal to conformal field theory, because it is indeed SU2 cross U1, the R-symmetry of these CFTs. So I'm going to show you a bit how the Gaiotto-Maldacena geometries look, and how one can establish a one-to-one map between a Gaiotto-Maldacena geometry and an AdS, a four-dimensional n equals 2 conformal field theory. So these are generic backgrounds dual to four-dimensional n equals 2 superconformal field theories. They are described in terms of a function that depends on the two coordinates of the Riemann surface. As I was saying before, this is the general form. The whole solution is a foliation over this 2D Riemann surface. So there are warpings that depend on the coordinates of the Riemann surface that are parameterized by this sigma and eta. In order to satisfy the supergravity equations of motion, this function V needs to solve a three-dimensional Laplace equation axially symmetric. So these solutions have been described in terms of electrostatic problems, because this is what you need to satisfy for this V function, which defines the solutions, because you can see here how everything, I'm now going to describe this in more detail, but everything depends on this V that needs to solve this equation. And you can compute in this equation, we have a cylindrical symmetry. The eta is along the axis of the cylinder and the sigma is the radial direction. You can define a line charge density along the axis of the cylinder, which reads like this. And well, it's computed at the axis. And this encodes a lot of the information that I'm going to discuss next in terms of regularity, quantization of charges, etc. The solutions look like this in terms of this V function. You have the AdS5 part, there's two, this is the Riemann surface, and then you have the circle. And you have the fluxes that said at the beginning that the V branes are charged with respect to some potentials that live in the string theory, in which these V branes live. In case we are the Lozano geometries are solutions that way supergravity, because remember that we are discussing CFTs that live in D4, D5, D6 intersections, and those even branes live in type 2A string theory. So we find the Ramon one-form potential. Its field strength is a two-form, and the D6 branes are magnetically charged with respect to this one. The Neves-Schwarz 5 branes are magnetically charged with respect to this field, V2, which is the one the fundamental strings are electrically charged with respect to it, and then the D4 branes are magnetically charged with respect to the field strength of this C3. But you see that everything depends on V, and this is the dilaton. This constant is what the expectation value gives the string coupling constant. Anyway, these solutions, one can establish a one-to-one map between the solution and the four-dimensional superconformal theory. But this is far from obvious for this particular, yes? No, it doesn't have to be. This is there are other AdS5 solutions in which here you have a Sasaki-Einstein manifold that can be an S5 or something more general, and those preserve less supersymmetries than these ones, typically. I don't think here this is it has any Sasaki-Einstein structure, I think. Huh? Yes. Yes, no, this is another class of solutions that are also very interesting for other reasons, but don't live in Hanani-Witten brane intersections. So I'm going to show you how far from trivial is to establish the one-to-one map between an AdS5 solution in the Gallotto-Maldacena class and the four-dimensional n=2 CFTs that live in the Hanani-Witten brane setup. Yes. Yes, it's a Laplace equation. And I'm not going to talk about boundary conditions. They are hidden in my next slides, because this is, in fact, the whole complication of establishing the one-to-one map. And it's quite technical, and I thought that illustrating this with this example would take too much time. So I'm going to just tell you how it goes. And then I will illustrate how you establish a one-to-one map with another example in which it's much simpler. This is very interesting, but I I think that, yeah, not so easy to see. So indeed, you have to impose in your solutions regularity and the quantization of charges. And you can see that these boundary conditions, you can formulate them as the boundary conditions for your electrostatic Laplace equation. And this impose strong constraints, in particular on the line charge density. That is what you use in order to define these constraints. So what I am skipping here is how you get into these conditions, basically. Because this essentially is regularity and quantization. Tells you, the quantization of charges, that this function, lambda of eta, must be a piecewise linear continuous function. It must vanish at the place where you take the beginning of the space in the eta direction, that we took it at eta equals 0. It needs to vanish also at the end, if you want to have a compact space. This, I didn't write it here because sometimes you work with So basically, you have like profiles of this type in which, in the end, the whole thing is going back to 0 in a piecewise linear way. Then the slope must be an integer, always decrease, and it can only change at integer values of eta. And then each time the slope changes by k units, you find k by one singularity, one type of singularity that is associated to the presence of these 6 branes, because these 6 branes introduce singularities in your geometry. So for example, this would be a valid line charge density that would give rise to a solution that is regular and that has quantized charges. Let's see how from here you read the information about the conformal field theory dual to this solution. SUNI gauge group is associated to each integer value of eta equal eta I, with Ni given by the value of the line charge density at this integer value of eta. This gives you the rank of the gauge group. Then a kink in the line profile corresponds to extra Ki fundamentals attached to the gauge group at the node Ni. So in our example, we have when eta is 1, the value of lambda is 4, so this gives us a gauge group with rank 4. When eta is 2, a gauge group with rank 5, when it's 3, 6, and when it's 4, 7. Then there are changes of slope that happen here from 4 to 1. So here we have to add 3 D6 branes, 3 units of flavor group. And there is another jump from 1 to 0. Here we have to add 1 flavor group. Here in this construction, you see automatically how twice the number of colors, 8, is the sum of 3 plus 5. 2 times 5, 10 is 4 plus 6. 2 times 6, 12 is 5 plus 7. 2 times 7 is 6 plus 7 plus 1. So with this construction, you are building automatically a quiver that describes a conformal field theory. It satisfies the right conditions. Okay, getting into here is the non-trivial part. Once you know the rules, it is very easy to find what is the dual field theory to a given solution. And here I didn't terminate, but you should care about terminating the space. And one way in which you can do it is this other simple construction. Here I have reintroduced units because you need to have that the ranks of these gauge groups, that here I just put 4, 5, whatever, the ranks have to be large because this is when your supergravity description is valid. Remember, like the second transparency also. So here I have restated this N6 and I have used a very simple profile for the line charge density in which you just have a line with the same slope all the time between 0 and p minus 1. This is going to give us a chain of gauge groups from with ranks N6 to N6 till P-1, N6 with no flavors because there is no change of slope. But then in this example, I cared about closing the space. I am here gluing this line with this other one in which I'm terminating the space with a vanishing of lambda. Here we have a change of a slope by P units, something like this. And this means that we are introducing this flavor group. And in this way, you make sure that you satisfy conformal invariance also in this last gauge node, because 2 P-1 and 6 is P-2 and 6 plus P and 6. Okay, now in these examples, you can test the holographic correspondence between the AdS5 geometry and the quiver, the conformal field theory described by this quiver. For instance, computing the central charge on both sides and seeing that they agree. I'm not going to show you that here. I will do it in another example in which this is simple.
Normally, I think of seeing the local symmetries of the local symmetries of the AdS.
Mm-hmm. It as a singularity. This you see it because you are terminating the space with these 6 branes, and then you see the presence of these 6 branes at the end of the space. Yes. And in the other cases, this is a good question. I was not planning on going into these details, but of course, when you have these 6 branes in different places, not at the beginning or the end, you also have their localized singularities. They appear in the Bianchi identities as delta functions. Okay, just to give you a flavor of what happens in other dimensions. For instance, you can build a 6-dimensional field theory with this Hanani-Witten brane setup in which you have D6 and S5, D8. Now they intersect on a 6-dimensional surface, which is where the field theory lives. And the D6 are stretched between the NS5 branes in the same way I was showing before. In this case, the same kind of analysis tells you that you have vector multiplets coming from the D6 branes. In this case, this defines a 6-dimensional Yang-Mills theory that is built in terms of 60 1,0 vector multiplets and hypermultiplets. It turns out that here this theory is chiral, so you can define a chirality matrix, and all your fields, the matter content, can be written in terms of these chiral fields. These theories, we now have a 6-dimensional field theory. So this will not be conformal. This will be conformal in the UV. And even for that to happen, there are some conditions that need to be satisfied. In this case, what you do is enforce that the Weyl anomaly is vanishing. This is what guarantees that this can flow to a CFT in the UV. Again, I'm not giving the details of this. It's a lot of stuff. But in the end, the condition is the same as before. So the kind of quivers that we are going to draw are similar to the previous one. The reason is different, but the analysis is very similar. The holographic duals of these 6-dimensional conformal field theories were found by Tomasiello and collaborators in 2014. In fact, it was not found, I mean, they just classified the most general classes of solutions with an AdS7 in type 2a supergravity. And they are solutions of this type, AdS7, S2, and they are fibered on an interval. The global symmetry of the S2 is SO3, which is SU2, and this SU2 is the R symmetry of the 6-dimensional CFT. So this was already suspicious that these theories could be the holographic duals of the 6D CFTs. And in fact, Gallotto Tomasiello and Cremonesi Tomasiello proved that and established the one-to-one map between the geometry and the solutions, and the CFTs. In this case, this is much easier to see than with the Gallotto Maldacena, because essentially you have an interval in the solution depends on a function now that only depends on one coordinate instead of two. This makes the analysis much simpler. The general form, you have the AdS7 part, the interval, and the two sphere. And the solution depends on this function alpha, which is the function of Z. So you have also the dilaton, you have the Neves-Schwarz-2 form. Remember the NS5 branes are charged with respect to this one. You have an F2, this is the field strength of the Ramon-Ramon 1 form. The D6 branes are charged with respect to this one. And then we have an extra parameter, this F0, which is a constant, and is what is called the mass of type 2A supergravity. When you have it switched on, you are talking about massive 2A supergravity. This is why. And the objects that carry this charge are D8 branes. So here we have D6 and S5 D8. As was shown in the brane setup. So this function encodes the information of the dual CFT, and there is a one-to-one mapping that was established in this paper by Cremonesi and Tomasiello, showing how from a particular profile of alpha, you construct the dual gauge theory that flows the UV to the CFT dual to this solution. An example, which is the same quiver I showed you before for the four-dimensional superconformality theory. In this case, is for the six-dimensional one. Here, six-dimensional vector multiplets, six-dimensional hypermultiplets, etc. In this case, the function alpha had to be cubic because you see that the third derivative must be a constant. But you can make it cubic in a way that the third derivative jumps. Every time it jumps, you are introducing a number of D8 branes, because this is how you change this mass parameter, introducing D8 branes. So here I chose to do something much simpler from 0 to P. We just have a cubic profile that is continuous even in the third derivative. But then I jump in the third derivative in this way, closing the space. Again, this guarantees that alpha at the end of the space closes because this is how you do it in this example. This introduces the 8 branes at the end of the space before you were introducing the 6 branes. This is dual to a linear quiver with this gauge group because you are not introducing the 8 branes anywhere from 0 to P. Then in the end, you are closing, introducing the 8 branes here. There is a jump in the third derivative. This is non-anomalous, and this will flow to some CFT in the UV, which would be dual to the AdS7 solution. Okay, let me mention something about 2 dimensions. I'm focusing on the even cases because I don't know why I just chose this. I think they are a bit simpler. In this case, in 2 dimensions, we are interested in 2-dimensional conformality theories, and this will be dual to AdS3 spaces. In this case, the maximum number of supersymmetries that can be preserved by an AdS3 space is 16, is not 32. This is what we call maximally supersymmetric when we are in 2 dimensions or in talking about AdS3. And the first solutions that were constructed with this containing an AdS3 were already in the seminal paper by Maldacena, this AdS3 times S3 times Calabi-Yau 2. This is a 4-dimensional surface that has that is Ricci flat. And this straightforward variation of it, which is orbifolding or modding out this S3 by this discrete group. This reduces the supersymmetries. In this case, we have the 16 supersymmetries. In this case, we have 8 supersymmetries because this reduces the supersymmetries by a half. So you may think why you are not considering just the D1 branes to try to discuss a conformal field theory living in D1 branes. This is not possible because the D1 branes are described by two-dimensional supergeometries, but this flows in the IR to a trivial fixed point. So this, you don't get a conformal field theory from there. The next thing that people tried was to superpose D1 and D5 branes. This breaks the supersymmetries twice, so we have the 8 supersymmetries. And together with the superconformal generators, this would give you 16, which is the supersymmetries preserved by the AdS3 by this one, because in fact, the system in the near horizon gives the AdS3 cross S3 cross Calabi-Yau2. So this is where this geometry is realized. If you add this effect, this modding by CK is done by introducing what is called a gravitational brane. A Kaluza-Klein monopole is a particular solution that is also called brane because it has some spatial dimensions whose effect basically is well, to do this modding and to break by a further half. These are not Hanani-Witten brane setups. You have the 1D5, you have the 1D5 KK, but if you do a T-duality into type 2A, and this T-duality is some symmetry that you have in the superstring theories of type 2, by which you can realize the string theories propagating in a given space-time in type 2B, for instance, with a string theory propagating in a similar, in a T-dual space-time in type 2A. And those propagations are fully equivalent. Yeah, I'm going to that precisely now. In this case, you have AdS3 times S3 times Calabi-Yau2. The S3 is a Hopf fiber, an S1 or an S2. And you take this S1 to do the T-duality transformation. In which case, you arrive to a space which has AdS3 times S2 times S1, but now direct product, there is no vibration, times the Calabi-Yau2. And this space that is in the type 2A theory is the strings that propagate there is completely equivalent to the strings that propagate here. Normally, many times you play with these dualities because it is easier sometimes to address certain properties in the T-dual space.
What is the effect of the origin of vibration?
The vibration creates an NS5 brane. I can show you, I mean, there are rules, the Busser rules that tell you how specifically the geometry is mapped in this T-duality transformation. And well, there is an inversion of the radius, and there is some mixing, say, into non-diagonal components of the metric, as this the connection that you have in the description of S3 as a Hopf vibration, that becomes a B2, a Neves-Schwarz to form, like the ones that I was showing before. It becomes now torsion, and then S5s are charged with respect to this one. So the effect is to introduce an NS5 after you did the T-duality. So in fact, I was going in that direction because I was saying, well, here I don't have any kind of Hanani-Witten brane setup, but if I do a T-duality, the T-duality will make the NS5 appear. Also, it is known very well how the D-branes are transformed under T-duality. If you have a D1 brane, this becomes a D2 brane. If you have a D5 brane, this becomes a D6 brane. And they are wrapped on the circular direction in which you perform your T-duality. So in type 2A, you indeed have a Hanani-Witten brane intersection that gives a two-dimensional theory in the intersection. In this case, the D2s, well, this is not, sorry, because I'm going to, this is not a typical Hanani-Witten-Brane intersection because we have the extra D6s. It would be a Hanani-Witten-Brane intersection without the flavor D4 branes if the D6s were not there. But, and I'm going to discuss other examples of this, of Hanani-Witten brane intersections in which you have two types of color branes. And this is what happens here. You don't have any flavor branes, but you have two types of D2s and D6 stretched between the NS5s. Here, this direction is not an interval, as I was showing before, but it's a circle. It's the result of a T-duality. And what happens is that the NS5 is located in one point of this circle. You have the NS5 and then the circle, and the D2s and the D6 stretch between the NS5, the only NS5 that you have, along this circle. So this gives you a quiver that looks like this, because you have the D2 branes that I said are colored. You have the D6 branes that are also colored. Both of them are stretched between the NS5, and then the bifundamentals that would come across the NS5 become fields in the adjoint of the corresponding gauge group. Okay, so this is the kind of quiver that you obtain because there are then massless fields coming from the open strings that connect the D2 and the D6. I'm not going to explain this here because I will explain it later in a wider class in which this example is included. If you had this other solution where you are introducing this modding, you have to introduce to achieve that K Kaluza-Klein monopoles. And this, after the T-duality, give you K Neves-Schwarz 5 branes. So in this case, in the circle, you have K NS5 branes located along the circle with a number of D2 branes and D6 branes stretched. And now you have bifundamental fields all along this circular direction. This is the kind of quiver that you find here. The interest of these solutions is that the conformal field theory, which is quiver theories flow in the infrared, in this case, has been very much studied and has been identified as the symmetric product orbifold CFT. In other cases, the theme flows to some CFT in the UV, in the IR, that is not so well known. Okay, in these type 2A realizations, these solutions are particular examples in a wider class of solutions, which are of this type. AdS3 times S2 times Calabi-Yau2 times interval. What I discussed, the solutions are in this class when I is an S1, but it can be more general. And this is what I'm going to discuss next. Next, I'm going to review these solutions, and I'm going to use this as an explicit example in which I will show you how from an AdS3 solution you can construct step by step, which is the dual quiver theory, and what you can expect to find in the IR in this case, because we are in dimensions less than 4. I don't know, I probably have 10 minutes. What time is it?
Oh, sorry. 12. Sorry.
Who are you if I continue? Okay, so maybe I'm going to be a bit fast here. I wanted to show you an explicit example in which I was involved, but the reason to choose this example is not because I was involved, but because I think it's a very simple one in which you can see how from the geometry you can construct the dual quiver. So this is a class of solutions which preserve 0 for supersymmetry. It reads like this. So these are solutions in 2A supergravity in the massive extension, because we will have D8 branes And there are two types when M4 is a Calabi-Yau-2 or a Keller manifold. Here I'm going to be interested in the Calabi-Yau-2 case. This is the class that I was mentioning. Well, not the class. This is the class to which the solutions that I mentioned before, doing T-duality from AdS3 cross S3 cross Calabi-Yau-2 belong. Okay, but now this is when the interval is a circle, but here we will be more general, and this interval can be anything. Yeah, no, the other class is more general, and it includes Keller, and it includes Calabi-Yau as a particular case. Sorry. It is also possible that it is a Calabi-Yau there, but the class of solutions is quite different. Yes, I always forget to remark that, but you're absolutely right. So in the first class, the geometry looks like this. You have the AdS3, you have the S2, you have the Calabi-Yau-2, and you have the interval. This class of solutions is labeled by these three functions, U, H4, and H8, which have to satisfy some conditions for this to be a solution of the supergravity equations of motion. U and H8 need to be linear functions in rho. Well, they are all functions of rho. The only coordinate that is not, well, not exactly. The H4 can be a function of rho and the Calabi-Yau-2, but the examples that we discussed in detail in order to construct the dual field theory are those in which the Calabi-Yau is compact. So in this case, H4 cannot depend on the Calabi-Yau, it depends on rho and it depends linearly. Or T4. No, both the T4 and the K3, even if one is very simple and the other one is much harder too, they lead to the same physics actually. And the same number of supersymmetries. And here the important thing is that this will act as you have there a compact four-dimensional manifold, you will integrate over it, and the volumes of the T4 or the K3 is what will appear in the end in the quantized charges, but there is no difference between them. So we take it to be compact because we want to have a compact space because we aim to find a well-defined dual CFT. So we took the compact case, and in that case, H4 is a linear function of rho. And we simplified with this U function, which does not have a physical meaning, we put it to 1 or something. Well, here you have a non-vanishing V2, which is such that you have 1 NS5 at different positions in rho. If I have time, I will show the explicit form of V2, but at this point, I just want to convey that as you move in rho, and we chose the normalization in this way, you are positioning NS5 branes in the geometry. And then you have the field strengths of these different fluxes that live in string theory, which upon integration give you the quantized charges of D branes. In particular, this constant thing, which depends on the derivative of H8, as H8 was linear, this is a constant, gives the 8 brane charge, the F2 gives the 6 brane charge, F4 gives the 4, and F6 gives the 2. So we have all this intersection. You may think, how can this be a simpler example? Well, it is because even if we have two families of color and two families of flavor, in the end, these functions are linear, and this is what makes the analysis much simpler. So we actually could construct the explicit brane intersection that gives the near horizon geometry AdS3 times S2 times everything. And there you see that the D2 and D6 branes are stretched between the NS5 branes along the rho direction. So they are the color branes, the branes where the gauge fields live. The D4 and the D8 are perpendicular. They play the role of flavor branes. This is supported by the analysis of the Bianchi identities, what I was telling Emmanuel before, because these ones will appear as sources, as point-like singularities in your Bianchi identities. So the brane setup is a Hanani-Witten brane setup of this type, with D2s and D6 stretched and D4s and D8s perpendicular. These D6 effectively are like D2s because they are wrapped on the Calabi-Yau, and I have taken the Calabi-Yau to be compact. So if we take it to be a string size, these branes are exactly as heavier or lighter as the D2 branes. And the same thing with the D8s and the D4s. Now here one has to look at the quantization of the open strings with both ends on the D2s across NS5, the same with the D6, D2 across NS5 to the D6, D2 to D8, D2 to D4. There is like a whole variety of things that you have to explore. But this has been studied, so you can just, you know what the quantization of the open strings gives. So in this case, we are going to build quivers in which our circle will be representing a 0,4 vector multiplet. I said that these theories preserve 0,4 supersymmetry. So the field content is encoded in 0,4 fields. This circle will have 0,4 vector, but it will also have a 0,4 hypermultiplet in the adjoint. This is because for these multiplets, the scalars are not part of the vector multiplet. They come in a separate one. These are technical things. Then we will have lines in the fundamental or bifundamental that will describe 0,4 hypermultiplets. Others will describe 4,4 twisted hypermultiplets. This twisted means that the scalars in this hyper transform under their symmetry. This is what distinguishes the two of them. The 4,4 twisted is built of a 0,4 twisted and two 0,2 Fermis. This is a surprising thing when this appears in this kind of quivers, the 0,2 Fermi. And this is because this is a left moving fermion, and you say how this left moving fermion appears here. Well, it doesn't have a supersymmetric companion because it's left moving and there is no supersymmetry in the left moving sector. But this fermion is very important in order to build a superpotential. Still, the supersymmetry determines how it interacts with the right moving fermions, and it plays an important role in the construction of the theory. So here I just, for the record, mention from which kind of open strings the different vector and matter fields there appear. From D2, we find the 0,4 vector and the 0,4 adjoint, and from D6, D6, meaning strings with both ends in the same stack of D2 branes or in the same stack of D6 branes. When they are across an NS5, we find the 4,4 twisted for D2, D4, and D6, D8, and the 0,2 Fermi basically comes from branes that are completely orthogonal, and there are no scalars that can be excited, say, there is no room for them. So they just give a fermionic mode. So these theories are chiral, and in this case, you have to be careful that the Gates anomaly is cancelled. And for that, you need to look in detail at how the different fermions in the different multiplets contribute to the Gates anomaly. Okay, there is this table here that tells you how they contribute, the number of fermions in each of the multiplets that are here. There is also the R charge, because this will play a role later when I compute the central charge. But here, the cancellation of the Gates anomaly is the important thing. And you can see for a given Gates group with rank n, if it is connected with others that can be Gates or flavor, with twisted hypermultiplets or 0,2 Fermi multiplets, you can see how the corresponding fermions contribute to the Gates anomaly. You do your calculation and you arrive to this condition equal to 0. This thing there should be a 0. So this part of the quiver is the one that affects Gates anomaly, because this other part, remember this was 4,4, this part is non-chiral, we don't have a problem, and the contribution of the 0,4 vector and the 0,4 hyper in the adjoint cancel each other. So it is this part of the quiver that tells you, that gives the condition that the gauge anomaly has to cancel. Now, once we have an anomalous quiver, we can compute the central charge because from the superconformal algebra, you compute the central extension of the superconformal algebra, which is the asymmetry anomaly. This happens to be the central charge because the energy momentum tensor and the R current sit in the same multiplet. So this is the way in which this is related, and the K is the asymmetry anomaly that you computed from the charge of the fermions under the asymmetry. The asymmetry was SU2 that I forgot to say, but this is what the geometry is telling you. Here you have an SU2 and there are no other symmetries coming from other parts. And this is indeed the asymmetry of the CFT theories. So you compute this. If the table before would tell you that only the hypermultiplets and the vector multiplets contribute, the gamma 3 induces this minus in the left moving ones, which are the ones in the vector. So this is what you find. So you have a very compact expression to compute the central charge in the field theory. Now, how you construct the quiver from the AdS3 solutions, you just use your fluxes to compute the number of branes in each interval. From the NS5 branes, you find that this is the expression of the V2 field for rho divided in these intervals. You have to compute this taking into account that V2 always has to satisfy this condition. It has to be in the fundamental region. Otherwise, Gates equivalent configurations will contribute an infinite number of times to the partition function. And for this reason, when you, it just depends on rho, if you abandon the fundamental region, advancing here in rho, you need to perform a large Gates transformation to bring it back to satisfy this condition. This physically is telling you that you are introducing NS5 branes as you move in the rho direction. Then you compute the D branes using the usual formula with the field strengths that we had from the solutions. Of course, to compute this, we need to have the specific form of H4 and H8. We take them to be piecewise linear, such that each time there is a jump in the first derivative, we are introducing with the H4, we are introducing D4 branes, and with the H8, we are introducing D8 branes. But then the mu's and the alphas have to satisfy continuity conditions because H4 and H8 have to be continuous, and this is the condition for them to be continuous. Then you impose that the space starts and ends properly in 0 and in 2 pi p plus 1 as we have chosen. There you impose that the two type of functions vanish. This is a singularity that is interpreted as a superposition as D4 and D8 branes. So this is perfectly possible. And now you take into account that the holographic limit will be reached when the ranks of the gauge groups are large, because this alpha k and this mu k will give you, when you do these integrations, the number, the mu k will give you the number of D6 in each interval, and the alpha, the number of D2 in each interval. So this has to be large, but also P, the size of the interval, has to be large, because we need all these sources, the D4s and the D8s that appear in each interval, to be well separated. Otherwise, they will back react in the geometry and modify the solution. So this is part of the regime in which the supergravity limit is valid. Now I can show you the quiver with the specific charges in each of the nodes coming from the solution. And we can check that it is non-anomalous, because if we choose, for instance, the alpha k, the alpha 2 node, R is mu2, is the one connected with a 0,4, and Q coming from the fermions is mu1, mu3, and then mu1 minus mu2. And this is exactly satisfied taking into account how the mu's were obtained from the mu's. So automatically from the solution, this is anomaly free, the quivers that you can construct. They can flow to a CFT in the IR, and the CFT will be dual to the solutions. You can check this duality computing the central charge from the field theory using this expression and counting the number of hypers and the number of vectors in this quiver that we have here. This gives you this expression. And now you can compare this with the central charge that you compute from the geometry using the brane formula. This was derived for AdS3 spaces as we have, and it depends on the radius of the AdS3 and the 3D Newton's constant, which is the 10D Newton's constant divided by the volume of the internal manifold, and this is how this appears. You put here the H4 and the H8, and you get the same central charge. So this is a check that these quivers are indeed related to the solutions and will flow to a CFT dual to them. And since I went over time by I don't know how many minutes, I will just mention very briefly to finish here, because you may wonder what happens in other dimensions. In other dimensions, you have, for instance, in 3D, the Hanani-Witten-Brane setups would be the 3s stretched between NS5s with this was the original Hanani-Witten-Brane setup discussed by Hanani and Witten, and in some theories can flow to conformal field theories, and the AdS4 duals were identified in this paper where they established the one-to-one map. They belong, these classes, to a classification previously found by these people here. In 5D, this is also known. These are the 5s stretched between NS5s with the 7s perpendicular. This is one of the samples I was mentioning in the introduction that took a long time to identify, even to construct the AdS6 solutions dual to them, because this classification of AdS6 times S2 times sigma 2 solutions in type 2 string theory is from 2016. And the one-to-one map with the conformal field theories that arise in this case in 5 dimensions from the Hanani-Witten-Brane setup was established in these papers quite recently. In 1 dimensions, one can construct the ones stretched between the NS5s with the 3s orthogonal, and by the symmetries, you know that the duals will be in a classification in another paper of the same people. But the one-to-one mapping has not been established. So this is the status, because you cannot have things in dimensions higher than 6. In that case, you don't have supersymmetric AdS spaces and you don't have a superconformal algebras. So I will stop here. Sorry.
What's the role of the inner of matter?
Well, in these examples, in both cases, here and here, this has not been analyzed in much detail, but in these other cases, people have considered Riemann surfaces, which were the infinite strip, just an infinite strip, or the annulus, in which case you have one compact direction, a circle and an interval. But other than this, to my knowledge, I don't think this has been explored. In the Gallardo-Maldacena case, it has, because there, when you want to describe, for instance, the Maldacena-Núñez solution, there your Riemann surface has to be a hyperbolic surface with a given genus. In 4D CFTs. So you are referring to the Gayotto-Maldacena case. In this case, you are referring to field theories, which I didn't discuss here, because these are the Gayotto theories, which are non-Lagrangian and strongly coupled, intrinsically strongly coupled. And those theories are associated to M5 branes. You normally look at the description in 11 dimensions that are wrapped on a Riemann surface, and this Riemann surface can have different genus, and this genus is captured in the AdS5 dual by this 2D Riemann surface. Yes. Yes, I skipped that on purpose because it's more complicated to. In the 1D, you have D1 branes stretched between NS5 branes with perpendicular D3 branes. This is supposed to preserve 8 supersymmetries. And by looking at the isometries of the S4 and the S2, which is SO5 times SO3 or SU2, there is a superconformal algebra which has this asymmetry. So, I mean, this would be the superconformal algebra that arises in the IR from these brane intersections. But this has not been studied in much detail. I mean, there is no one-to-one duality in this case.